So let's first recall what we did in the last class. In the last class I started by sort of saying we are going back to history because there is good reason that we want to go back to history. We want to go back and say at homes we want to use DC power line rather than an AC power line. What are the reasons that I mentioned that we want to use DC power line? The primary reason was every appliance is gradually shifting to DC. And it is not just shifting to DC. As it is shifting to DC, its efficiency is increasing very significantly. Let's recall what are the appliances that I talked about. First we talked about electronics. All electronics uses only DC power and not AC power. So every piece of electronics uses a AC to DC converter when I am trying to power it using AC. A television today uses AC to DC converter, a laptop uses AC to DC converter, a speaker uses AC to DC converter, a cell phone uses AC to DC converter, and practically everything, even every sensor in fact. What is so surprising is that you go to these hotels or restaurants where they have automatic wash and you put your hand and there is a sensor which detects, and the sensor of course is electronics, uses only DC, but there is a AC to DC converter built in. So we have AC DC, AC DC converter. Each of these AC DC converter of course costs something. Number two, consumes power, have losses, and therefore your overall efficiency goes down. It may even impact power factor. I did not emphasize that sufficiently, but I hope in some of your classes, your teachers, your local teachers will start looking at power factor impact. It's also a point of failure. If that fails, the powering fails. So all electronics has that. Then I saw say it's not limited to electronics. All displays, well, displays are electronics. Well, they started with the CRT displays and all that, which is using large power, but it has all come to LCD and LED display today. Every LED that is used anywhere uses only DC. And LCD and LED display, the display that you are seeing my picture is all DC. Then we talked about lighting. Lighting did use AC till recently. In fact, the old tungsten bulb used AC. Even the CFL, fluorescent light, was used as AC. CFL used AC. But as soon as we come to LED, it's all DC. And lights in future is going to be all LED, or something new may come up, and it will be all DC. And then finally I came to the very, very important thing, motors. And I spent some time in talking about motors and what a DC motor was, what was a AC induction motor, and the world is dominated by AC induction motor, except now with the power electronics, the brushless DC motor and SR motors are coming far more efficient, particularly as you decrease the speed, as you change the speed. It's a DC motor, BLDC motor or SR motor which gives you far more efficiency, higher efficiency. So what did it mean? I talked about a fan. A fan consumes 40% of the power, 40%. AC fan consumes 72 watts, a ceiling fan, an equivalent brushless DC motor fan consumes only 30 watts. And at lower speed, you get even larger advantage. But motor is not just fans. Your cooler, air cooler that you use, if you live in a dry weather, it is all a fan, a motor, essentially uses a motor. A refrigerator primarily uses a motor. Of course, motor is a part of compressor, but finally powering is done to the motor. Every pump uses motor. You use not just pump, but you use pretty much anything, you use a motor. A mixer uses a motor, a washing machine uses a motor, and all these things essentially if you shift to DC, it gives you a huge advantage. So it may soon happen, in fact that's true for microwave ovens. I am less familiar, but I am told induction heater again uses DC. So very soon there will be no appliance at home which will use AC power directly. Of course, you can always continue to use AC power lines and keep on using AC to DC converter and power these or move to a DC power line. And it is this that I propose, that there is reason for us to move to a DC power line. I actually talked about two more things, but I did not elaborate that, and that's what the subject matter of today's lecture will be. The biggest renewable source, a rooftop solar photovoltaic panel. I can put it on my rooftop, so whenever sun comes out, it starts giving you power. One of the greatest things, completely decentralized, I can produce my own power on my rooftop. I don't need that big. We'll see, we don't need that big. Only thing is, it gives only DC power. We'll see that. It gives only DC power. It does not give you AC power. So if you use AC power, you have to do a DC to AC conversion again and synchronize it to the grid power. On the other hand, if you use DC directly, and that's what solar DC is, this whole thing is being built on solar DC, use solar directly in DC form. Then I talked about batteries very briefly. Storage. How is the storage done? The electrical power is converted into some kind of chemical energy and stored. How is battery charged? Using only DC power. So if you are using AC, you have to do AC to DC conversion and then only charge the battery. Similarly, when you use the battery, battery gives you out only DC power. If you are going to use AC, you have to again convert that DC to AC. So any time you use our AC power line at home, you will have a converter, a AC to DC converter for charging and DC to AC converter for withdrawing power from a battery. Two extra element of losses you add. Of course, battery has certain losses. Whenever you convert the electrical energy into chemical energy and vice versa, there is some losses. That losses you can't do much about it. Of course, the losses will vary depending on the kind of battery that you will use. And we will talk about it. This lecture, this set of two lectures, I'm going to primarily focus on these two very important things. One is solar panel, another is a battery. Get some understanding. You may already have some understanding, in which case I'm going to do a very surface level, top level, limited talk on solar panel. It is not a comprehensive talk on solar photovoltaic, nor is it a comprehensive talk on battery. But I want to give you a fairly good idea and explain what are the important parameters and discuss how do you charge or discharge and what is the role that AC plays and DC plays. Having done that, we are ready to build our solar DC system vis-a-vis AC system. We are ready to put a DC grid line at home and start connecting solar, connecting the grid or the mains, what we call, and also connect a battery and start driving the DC appliances directly. And we will talk about that as we move on. So let me start with a solar DC power. After all, solar cell, The key to a solar photovoltaic panel is a solar cell. What is it? It's a PN junction. It's a PN junction where whenever a sunlight or any other light is incident upon the cell material surface, the electrons present in the valence band absorb energy and being excited jump to the conduction band and becomes free. This diffusion of electrons from one material to another causes flow of current and thus converting the sunlight into electrical energy, into electricity. Very simple principle. You can get details of this in much more detail, and we will look at it. For example, this is a solar panel. If you take a photovoltaic effect, and if you see, if you just keep everything open circuit, there are holes which are moving around, electrons which are moving around. Of course, occasional electrons go out here, occasionally the holes go there, they cancel each other, no current flows. This is the normal situation. What happens? This is when there is no light, no light. Let me now add light and put a open circuit. Let's keep it open circuit, but I add light. What happens when I add light? The first thing that happens when I add light is you get more holes, more electrons, and the activity just increases. But remember that I have kept it open here. I have kept it open here, and because I have kept it open out here, therefore even though I have generated, there are more charges, but there is a voltage across terminals, but there is no current flow. And now what I will do is that I will short this. As soon as I short this, what happens? A certain amount of electrons will flow through this, come like this, and go into this. And this is the photoelectric effect that I was talking about. And this is what starts happening. Again, detail of this is fairly well known. Any device course will be able to teach you in much greater detail. I don't plan to get into the details of that. Let me, on the other hand, look at the way we want to use it. Let's look at this photodiode, and let's look at the circuit. What is the current flowing through this, and let us look at the voltage. And in the beginning, if I just keep it like this, then the current versus voltage curve is pretty much like this, that as I keep on adding a certain amount of voltage, a current will start flowing, and when I add light, so this is what happens as illumination increases. So this is what initially I have a photodiode. Let's take a photodiode, and what I'll do is that I will start. What happens? If I just take a photodiode, well, if I look at the voltage versus current, this is what the diode is. This is a simple diode principle. There is nothing IV curve of a simple diode. But suppose now I add to this photodiode, I add current. What happens when I add current? When I add a certain amount of current, the certain amount of current starts flowing, and the curve therefore shifts down. Why is it negative? Because the current that is going to be generated will flow in the reverse direction. So the current starts flowing, so the whole curve shifts down. Current versus voltage, that's what we get. If I add more light, now let's add more light. If I add more light, you cannot see it probably because it's yellow. There is more current that flows, and current goes more negative, and you get current versus voltage curve like this. And finally, since I want to represent I versus V, I reverse I want to represent I versus V, I'll represent it in this manner. This is basically IV characteristics of a solar cell. Now, this is again the same thing that I've drawn. I current of course always flows in the reverse direction, remember that, and that's, I have reversed it now. This is the direction in which the current flows because of the photocell versus V, and I get a curve like this, I versus V. So now I connect it to a load, a certain current will flow, certain voltage will be generated. I of course can operate at any of these points. At any of these points, I can keep on increasing the voltage. If I make the voltage small, then the current is this current, which is called the short circuit current of a photodiode. If on the other hand I keep on increasing the voltage, I get a voltage which is the open circuit voltage. Current becomes zero, because what happens? The current falls after a certain time. And if I keep on increasing the voltage, no voltage will flow. Now, the power generated is multiplication of the current into voltage. So, at any point, if I am here, my current is this, my voltage is zero, the power is zero. If I keep on increasing the voltage, well, the voltage increases, the current is more or less constant, and I will keep on getting larger and larger power. What happens? As I get larger and larger power, if I now reach this point, the current starts decreasing, but the voltage keeps on increasing, the power keeps on going up. After that, after this point, once I reach this point, what happens? The current is going to suddenly go down. So if I increase the voltage more, the power will also go down. So as a result, this power from the solar curve is something like this. And if you see, the maximum power point is this particular point. This is the maximum power point. This is the maximum power point. So this is the open circuit voltage, and this is the maximum power point. As long as I operate at this voltage, the current will be just below the short circuit current, voltage will be less than the open circuit voltage, but close to open circuit voltage, and I'll get maximum power point. This is called MPP, maximum power point, and very important. If you operate at lower voltage or higher voltage, then you will not get the maximum power point. So if you have bought a solar panel and you have put it on the rooftop, you have to ensure that the solar panel always operates at maximum power point. It is also called maximum power point tracking. Now why is it called maximum power point tracking? Because let's now look at the next important thing. The sunlight is not constant in the day. First of all, sunlight starts early in the morning, around maybe 6:30, depends on the place, 6:30, and 7 o'clock, in this particular case it is 7 o'clock. This is called insolence in watts per meter square. How much sunlight is falling on the solar panel, and it is defined in watts per meter square. So at some particular point it is fairly low. Around 7 a.m. it starts, because 7 a.m. the sun starts coming out. It depends on the particular day and the place. It may come early. If you are in Chennai, it will probably come out at 6 a.m. This may be from more like Punjab, where the sun comes out only around 6:30, 7 o'clock. So in the western part of India, so it comes and then goes up around noon, it peaks, and then it starts again dropping, and by around 5:30 or 6 it goes down to nearly zero again. So first of all, there is a solar insolence is like this, but even there it is not constant. Depending on the kind of cloudy day, it keeps on fluctuating. Why? Because a small cloud moves around the sun, it will dip, the cloud moves away, it goes up. So this of course is an actual solar insolence on a particular day, solar radiance, but this must be on a highly cloudy day. If you take good Indian data, it will be better than that, but still you will get a lot of fluctuations. So solar insolence is not constant. Now what happens when solar insolence is not constant? Look at this. So this was the original curve that I had drawn, V versus I curve, I versus V curve, I versus V curve. So this is the solar insolence, the red color curve is a solar insolence if the sun is at the peak. And I am saying it's 1000 watt per meter square. As long as is 1000 watt per meter square, it is this. So essentially what I am saying, at 1000 watts per meter square, it is like this. This is at 1000 watts per meter square. But suppose it is not 1000 watt, then it will be something like this. And if it is, so it is 800 watt per meter square, it is like this. And if you fall down further, it goes like this. All right. This is what it shows. So depending on the time of day and amount of shading, the V versus I curve will jump from here, will go on here, will keep on changing. Now if I look at the maximum power point, this is the maximum power point for this is the maximum power point, there is a maximum power point. So maximum power point does not have a constant voltage or a current. It keeps on changing. This is the voltage. Remember, this is the voltage. This is the current. So if I want to keep tracking maximum power point, depending the amount of insolence, depending on the amount of sun, I need to reduce the voltage or increase the voltage. This is called maximum power point tracking. If I don't do that, what will happen? Remember, let's go back to the curve here. If I don't do that, if my voltage goes lower, very quickly the amount of power that I will capture will fall down. So if I put a 500 watt solar panel, 500 watt, it is assumed that at 1000 watts per meter square, you will get 500 watt if you are operating at MPPT, maximum power point. But if you are not operating at maximum power point, you put a 500 watt, you may only get 300 watts, even if the sunlight is maximum. Very quickly it can fall down. So one of the key things that you need to do is keep on changing the voltage. You have to track. You have to keep on, small cloud comes in, you change the voltage. In fact, reduce the voltage to the maximum power point. Cloud goes away, you go back to the voltage. You have to keep on tracking. If you don't do that, if you just kind of fix it and run at one constant thing, so suppose you run at this constant thing, what will happen? At these points, at the peak, you will get a fairly close to the maximum power point, but most of the time when there is a little bit of shade, you are going to get very little power. 40%, 50% power may be lost. Look at this point. If I am operating at this particular line, look at this line, and if I am working at 200 watts per meter square, I am at this point where the current has fallen to half, voltage has slightly increased, I am getting half the power that I would have got if I would have left it to maximum power point. So this is extremely important. So I think one of the first things that in a solar panel one has to do is design to keep on operating at maximum power point. Now there are two ways to go about doing it. One way of course is that you put a feedback circuitry and keep on moving your voltage analog circuit so that it is at maximum power point. Alternatively, you could even do it digitally. You can keep on checking put a certain voltage, keep on shifting the voltage slightly, measure whether the power is going up or going down and keep on changing. But you need to do continuously. How often do you need to do it? Do you need to do every second? Yes, because power can change in second. Somebody says you have to do it more sooner than that, not even every second. Should you do it every few seconds? Well, if you don't mind a little bit of power loss, it depends on how much are you willing to do. If you really want to do it, you almost should do it instantaneously. So maximum power point is what you have to do. So that's the first thing that we need to do. what does it tell us? It tells us that if I take a solar panel and if I'm operating at a certain voltage, a maximum power point, this voltage will be not constant but changing with time. It will be changing with time. Changing with time certainly, because day, night, the morning, early morning to midday, that change will take place. But it can even fluctuate from instant to instant. Now that's extremely important. And I need to be at the maximum power point. If I don't operate within the maximum power point, then I'm going to lose a lot of power. And the voltage is changing. Now, it's a way, remember what I mentioned? I said, why don't we have a DC power line at home so that I can connect solar panel directly. But just now I have told that solar panel voltage needs to keep changing as per MPP. How are you going to then make that voltage equal to the voltage for your home wiring? Are you going to allow that difference? Are you going to put a DC-DC converter? Some people say just put a DC-DC converter. But the question that I ask, if I put a DC-DC converter, how much different it is as compared to putting a AC to DC converter? Small difference, yes, but you will still have losses. You are suddenly adding losses. Number two, not only you are adding losses, you are also adding a point of failure. You are adding costs. Whole idea of moving to DC was solar is DC, keep it at DC form. And therefore, it requires a fairly, it is a slogan will not do. Conceptually it is very good, but how do you synchronize a changing voltage DC solar line and make it synchronize with what the loads want? I think this is one of the challenge. I'm not going to completely present this, but these are the challenges that we need to really overcome. The second problem, I think that's another interesting problem. Look at these curves. If you see, let's say same amount of light is falling, 1000 watts per meter square. So light insolation is constant, and yet I get three different curves at 60 degrees centigrade, 45 degrees centigrade, 25 degrees centigrade. What does it say? It says if it's a 25 degrees centigrade, I probably will get more power, slightly more power than 60. But its voltage, maximum power point will also change fairly quickly. I may have maximum power point of 0.56 and I may have to make maximum power point of 0.50 for the higher temperature. Now, first one will ask, why 60 degrees? After all, temperature never goes up to 60 degrees. May go up to 45, yes, if you take a city like Meerut or city like Warangal in the summer month, or what is it, in Andhra Pradesh there is a place which gets very hot, the place there they do stone cutting, Kadapa, it gets very hot. But even then 46, 47, why am I talking about 60? The first important point that we want to make is that we are talking about the panel temperature rather than the atmospheric temperature. What happens? Atmospheric temperature may be 47. But in the panel, certain current will flow, certain heat will get generated, not all of that heat will get dissipated. As a result, the panel will keep on increasing, the temperature will keep on increasing. Depending on the time of the day, the panel can be 20 degrees centigrade hotter than the temperature outside, maybe 15 degrees. And this is the panel temperature that matters, because that's silicon wafer that is sitting there, the photovoltaic solar cell that is sitting there is at that temperature. Of course, some people say, what if I put blow air? Well, sure, blowing air can to some extent reduce. Somebody says, what happens if I put a water flowing through that? Well, water flowing through the panel, just below the panel, will absorb heat, and one can sort of say, well, I can do double. I can have solar panel generating electricity and then water and simultaneously water heater. Sure, that will increase your costs. Otherwise, you'll have to sort of say, well, temperature will vary and I have to worry about it. And I have given here the short circuit current, open circuit voltage, and here the power from maximum power point. It can vary at 10 to 15 milliwatt per centimeter square, or from minus 0.4 to minus 0.5 degree per centigrade. So, as the temperature increases, so you get minus 0.4%. So, if the 10 degrees increase, 4% lower power you will get, or 5% lower. No? We are a hotter country. If you are in United States or in Europe, the cooler country, they would get more power. The only advantage that we have is that we have far more sun than they have. They hardly have much sun. So it doesn't matter if we are a hot country. 5% is okay. We are going to get it for 12 hours. We are going to get it almost 325 days a year. And we get therefore a lot of sunlight, and solar PV works very well in all this. But you need to keep all these things into mind. You have to keep all these things into mind when you design that MPP, maximum power point, and how are you going to make it work. Now, so far I was talking about cell. Let's talk about cell forming a module. Now there are all these individual cells and you can connect them in series. What happens when you connect them in series? Well, the voltage will keep on going up, same current will flow, but as the voltage goes up, the power goes up. That's one way of going about doing it. Another is you put them in parallel. When you put them in parallel, what will happen? The current will go up. Voltage remains same. So the total voltage will be, if there are n cells connected in series and n in parallel, the voltage will be MVOC and current will be NISC. And for the module, therefore, the maximum peak current will be N into IMP and M into VP. So N into M, depends on number of cells. So just multiply by number of cells. Of course, you have to either connect them in series or in parallel and do it properly. Now, operating point should be such that the module operates at MPP. If it doesn't, there is a problem. It also presents a little bit of problem. What if the different cells have a slightly different MPP? It causes a problem. You have to worry about it, because then you can't keep on varying that. But this is essentially diagrammatically saying the same, that I can either keep on increasing voltage or current by putting them in parallel or in series, and I can combine any series and parallel, and therefore starting with one cell I can get multiple cell series and or multiple cells in parallel. Now what does it mean? It means that first of all I can get voltage that I want. I can get voltage that I want. I can roughly get the voltage that I want. Remember, if I know the maximum, I know the MPP voltage of one cell, and suppose I want 30 volts, I want 30 divided by VMPP of a single cell, that many number of cells in series. Remember, these are not open circuit voltage, these are operating point voltage. Now the reason I am also pointing this out is that sometimes somebody will say, this is a 12 volt cell, solar cell. What does a 12 volt solar cell means? 12 volt solar cell does not mean that the maximum operating point voltage is 12 volt. In a 12 volt cell, the open circuit voltage may be more like 16 volts and maximum power point voltage may be more like 14.5 or 15 volts. Now you need to figure that out. You can't just say 12 volt, because depending on what has been designed, you need an operating voltage, but that's what is going to be connected to your line. You need to find out the operating voltage. So this is what the example is, that you can connect them here, you can connect two of them in series. So one and 2 in series and 2 sets in parallel. From here positive goes like this, and like this, positive negative terminal. Essentially you can do an operating circuit for this, which is equivalently as if 2 are in parallel. So 6 volt 1.5 ampere and 6 volt 1.5 ampere, you finally land with 12 volt 3 ampere. But remember, these specifications that the panel manufacturer give you are not operating point. Operating point for a 12 volt solar panel will be typically 14 volts. If you take a 48 volt solar cell, operating point will be typically 55, 56 volts. So if you want 48 volt operating point, you need to get something like 40 or 42 volt solar cell. You need to worry about this. This is extremely important. Otherwise, so you have to design depending on what is the operating voltage that you want. And remember, operating voltage will change with temperature and throughout the day. So the question that you will ask is that what is the operating point voltage that you would like to change? So what happens is that most people don't worry about it. They say, well, whatever it be the voltage, operating point, this is the operating point voltage, operating point, and it will keep on changing, and I'll put a DC-DC converter and I get a fixed voltage, let's say 12 volt or 48 volt. One can do that, sure. One can allow this operating point voltage to change between 13 and 15 and can put a DC-DC converter. This will be a buck converter, not a boost converter. One can design a buck converter and one can get a 12 volts. Problem is you have introduced a loss element. Loss element, cost element and unreliability element. So don't worry, if you are willing to do that, live with that, it can be okay. But this is important, and I will come back to this loss element. But let's look at it. There are various other things that you need to worry about. One is a mismatch effect. For example, shading. Some solar cell may be shaded. Now what happens when some solar cell is shaded? That solar cell is not giving the voltage. And so your overall operating voltage can come down, or it may be that they are in parallel, but in one string they are shaded, in another string they are not shaded. What will happen? The two strings which are connected in parallel have different voltage. The current will start circulating. And these kind of things can create a lot of problem. So you get mismatched cells, hotspot heating. You don't worry about each of these things. When you design something, you have to worry about. You have to use a way to bypass the cell or not use the cell. Don't worry about these things. Cannot be given that you will always get that voltage. I'm not going to get into detail of that, but series connected mismatch cell, mismatch can be due to short circuit current, open circuit voltage and hotspot heating where the current starts flowing. Each of these things one has to worry about in designing this. Let me come to India and talk about what I am trying to sort of say. In India, we are lucky that there is plenty of sunlight availability. In most parts, there are few parts which are very, very rainy and all that. In most parts, it's between 325 to 300 days to 325 days a year. And typically about 12 hours a day. Now, how do you kind of characterize that? One of the way to characterize the solar, it is characterizing place, it is characterizing Chennai, it is characterizing Visakhapatnam, it is characterizing Madurai. How much sunlight does fall in a year? Pretty much constant, close to constant every year. Use that and say, suppose I take a 1 watt of solar panel. How much total watt will it produce? And you find the actual number in most of India vary from 1450 to 1650 watts. Now look at it. Suppose 1 watt was producing 24 hours a day. 1 watt was producing, I have 1 watt solar panel. Suppose it was producing 24 hours a day, then 24 watt hour it will produce. 1 watt should have done 24 watt hour. It is called watt hour. 1 watt, 24 hours if it was. And if it was kept 365 days, it should have been 365 into 24 watt hour. How much does it work out to be? 24 into 365. Can somebody give me the answer? 24 watt hour into 365. Huh? 8760 watt hour. Now this would have been there if 24 hours peak sunlight was available with no clouds ever. Now of course, first of all, sunlight is not available for more than 8, 10, 11 hours. Maybe 8 hours. You divide it by 3, 1/3 of it goes away anyway. So if you divide it by 3, in 8 hours every day, this is this much per year, would means 1/3 of that, which is 3 to the 6, 7, 9, 20, 2920. But then even 8 hours it doesn't fall maximum. Remember, it starts at very low, goes to the top and goes down. So what happens, it is like as if 4 to 4.5 hours it falls peak hours. So if it is a 4 to 4.5 hours into 365 days, it will multiply by 1450 or 1650 watt hours per day, watt hours per year. So very often say, well, sunlight may fall for 12 hours, but it gives you between 4.5 peak hours, equivalent to 4.5 peak hours, as if sun was available at peak for 4.5 hours. That's a total light that it gives you. Now also you have to face the sun, to always face it. In India you have to face it south facing at certain angle. I think in Chennai it is 11 degrees or 13 degrees, I don't remember. So depending on where you are, it is that 11 degree, 13 degrees is what you need to really make. You can't keep it flat. If you keep it flat, you will get less. Of course, you can track. If you are willing to do tracking and keep on making it face the sun, as the sun moves, the solar panel also is moving. Of course, that movement of solar panel will add cost significantly. If you add tracking, you will get probably 20% extra power. So you won't get 1600, you will get 1600 into 1.2. So almost 2000, 1920. But then the cost of tracking is significant. For small panel, you are unlikely to track. Okay. And remember that this should not be shaded. If there is a tree shade falling or anything else happening, you will get much worse. So solar sun, the way it is done, one sun is 1000 watts per meter square. But there is another thing that comes, and it's actually overemphasized because all of this is often driven by device engineers. For device engineer, the key question they will ask, what is the efficiency? They say 15% efficiency. What does 15% efficiency mean? It means 15% of the total sunlight that is falling on the sun, on the solar panel, is converted to electricity. Alright. So 15% efficient solar cell, by the way, 15% efficient solar cells are widely available in India. Solar panels cost 38 rupees, not so 38 rupees per watt power. So if you want a 100 watt power, watt peak, that's a peak, 100 watt peak panel, it will cost you around 3800 rupees. It produces 15%, sunlight is 1000 watt per meter square, you assume it is 1000, that's a peak. You will produce 150 watt per meter square when one sun falls on it. When one sun, which essentially means that if you 1 kilowatt power will approximately require 7 meters square. 7 meters square. If this 15% was changed to 20%, you would have been able to do 200 watts per meter square, and then you would have required only 5 meters square. So it depends on what the size of the panel is. how much roof space it occupies. 7 meters is approximately 3 meter by 2.2 meters. That you can get a solar panel which will produce 1 kilowatt, 3 meters by 2.2 meters, not that large. 1 kilowatt is 3 meters, 3 meters is roughly about this big, and 2.2 meter is, you can figure it out. That will produce 1 kilowatt. Today if it is as 15%, if you got it 20%, you will get it slightly smaller. You won't require 3 meter by 2.2 meters, you will require 3 meter into 1.7 meters. So area occupied, this percentage only makes difference as far as the area occupied is concerned. If you are short of area, sure it matters. If you are not short of area, it doesn't matter at all. Cost is not dependent, cost is dependent on watt power. You can get a 3,800 rupees a solar panel at 15% efficiency. Now R&D keeps on going up. Today R&D is available at 46%, it is available. 46%, this is of course in the lab. But for example, if you ask for 20%, 20% is easily available in the market. 20% will only take 5 meters square. Same 100 watt, 1 kilowatt solar panel will take only 5 meters square instead of 7 meters square. What will the cost? For a kilowatt, 1 kilowatt, it will be 38,000. For 15%, 38,000 will be the solar panel cost. So 1 kilowatt peak, our peak, 1 kilowatt peak, 1 kilowatt peak panel at 15% is rupees 38,000 at 15%. Suppose I want to buy at 20%. What is the cost at 20%? Well, I don't have the exact number, but approximately I can say 6,000 rupees, 60,000 rupees, 60,000 rupees. Cost more or less goes up by 1.7 times. No, almost more, 1.8 times. What do you gain? You get slightly smaller. So if area is not your concern, if you have enough, then it's of no meaning. This is today the 15% is most widely lowest cost. Lowest cost. In maybe 3 years, 5 years down the line, this will also be available at 38 rupees per watt. In which case you could buy that. It will take less area. So this whole percentage that we are talking about, efficiency, only tells how much area it takes. If you are not too bothered, in fact most homes which are going to put 200, 250 watt, if you do 100 watt, it will take 0.7 meters. 0.7 meters. What does it mean? 0.7 meter is 1 meter by 0.7 meter. 0.7 meter square. 1 meter by 0.7 meter. Now either 0.7 or 0.5, 100 watt if you want to put. How does it really matter? As long as you have that space. So very often this efficiency is overdone. Of course we want higher efficiency so that we can, given a roof space, I can put more and more solar panel. But then it costs more money and I may not be willing to spend more money. Even when it comes to 38, today I may need only 100 watts, so 100 watt may be enough. Or I may need 300 watts. 300 watt will require 2 meters square, 2 meter by 1 meter. What's the big deal? So it's a little bit overemphasized, and I want to point that out, a little bit overemphasized, and we don't need to worry about it. So this in fact kind of tells you what is going on. A huge, this chart is available to you in your PowerPoint slides. Please download it, otherwise it's unreadable. But you see large amount of research is going on all over the world, and every day somebody sort of say, well, efficiency I have reached 28%, somebody says I have reached 30%, somebody says I have reached 46%. Billions of dollars of R&D money is going into this. And frankly speaking, as far as I am concerned, I am not bothered. We have 15%, good, enough such things are available at this 15%. Cost is very low. I am a user, I want to put my DC power line, I'm quite happy. If I get 20%, what will it mean? It will only mean that I will use slightly less rooftop space. That slightly less rooftop space is probably not worth it. Okay, I want to emphasize that and say, as far as we are concerned, that efficiency, that does not mean much. The rest of things matter. Are we running it at maximum power point? Just because we get a better solar, higher efficient solar panel, it doesn't help me in making my things more efficient. It doesn't. It has nothing to do with the efficiency that I am talking about. I am talking about efficiency of if 100 watt of power is generated, how much power reaches load? Can I, if I am going to turn a bulb on or a fan on, how many hours will it last? If I put it into battery, how much will it last? The efficiency does not matter at all. I want to point that out. But if you are a device physicist, that's your job to keep on improving it. Why? It will mean with lesser space I will be able to generate more power. Okay? If you are making a centralized plant which generates a megawatt of power, now maybe that's where it matters, because 15% or 20% means so many acres less land will require. That's the only place it will matter, not for decentralized. Decentralized, if you are looking at powering rural areas, powering villages, powering homes, it's of not much significance. Okay? And if you look at it, whole policy is only towards how do you improve this efficiency. $1 billion in the world, probably more, is being spent on that. Within India, hundreds of, well, $1 billion is very small, hundreds of crore rupees goes within India for R&D in trying to improve. You can get something. Can you get it? If I can make 38 rupees cheaper, that makes a difference. Efficiency is not important. Can I make 38 rupees per watt to 30 rupees per watt? That will help. That is the R&D that we as system designer are interested. Okay? Alright? Now I will stop here for a few minutes. It's almost an hour I have taken, and this was a smaller lecture. To sum up, solar power panel produces only DC power, voltage and current throughout the day. Peaks during midday can be combined with AC grid using a maximum power point tracker. Inverter loss can be as low as 2.5% if I put 100 kilowatts. So if I put a centralized power plant, my inverter loss, DC to AC converter losses may be very small, 2.5%, 97%, 97.5% I can get. No problem. And the cost will be around 6 rupee 50 paise per unit. But suppose I want to put 500 watt solar panel on my rooftop, that DC to AC converter may lose 15% of the power. So I put 500 watts, 75, 80 watts goes away straight away. That's where my concern is, and that's what we want to optimize, and that's the reason we are talking about solar DC can feed directly to DC microgrid, but varying voltage needs to be handled, and the cost can be as low as 4 rupee 50 paise per unit. This is including interest costs, including everything. All right. I'll stop with one question only, a very simple question which everybody will be able to answer, and which is the call is GCT. I'm sure GCT will be able to answer this, and I want this class to answer. What is the correct combination? I want to design 48 volt 40 ampere, and I have 24 volt 10 ampere. 24 volt 10 ampere I have got 24 volt 10 ampere. How many in series, how many in parallel? So I've got 24 volt 10 ampere, 24 volt 10 ampere I've got, and I want 48 volt 40 amperes. Very, very easy question. How many in series, how many in parallel? The first answer is A, 4 in series, 4 in parallel. Anybody says yes? Second answer is, please GCT raise, Coimbatore raise hand for A. Is anyone says yes for A? B, 2 in series and 4 in parallel. Anybody who raise hand for 2 in series and 4 in parallel? Anybody here raise hand for 2 in series, 4 in parallel? I don't see anybody raising hand even. The question C, 4 in series and 2 in parallel. What will happen if I put 4 in series? I'll get 24 volt into 4, 96 volt. That's not what I want. So C cannot be the right answer. Anyone say C is the right answer? D, 2 in series, 2 in parallel. 2 in series, 2 in parallel is good because 24 volt into 2 is 48 volt. GC Coimbatore. Which one is your right answer? A is right answer. Raise your hand. Anyone believes A? Anyone believes B is the right answer? Nobody believes B is the right answer. I see a teacher trying to raise hand. Ah, now teacher is, everybody is following the teacher. Wow. Anybody believes C is the right answer? I still see 1, 2 hands up. Are they old? Everybody has put it down. D is the right answer, not teacher, one student. Can you ask questions, please? Now, yes. Questions to you, GCT Coimbatore.
Sir, how we increase the efficiency of solar panel?
How do we increase the efficiency of solar panel? First of all, I just told you that solar panel efficiency really doesn't matter. But yet, if you are interested in that, you need to do device physics. Today, if you make a silicon, monocrystalline, you don't get good. You do multicrystalline, you get better. You have to put probably germanium, sorry, not germanium, gallium arsenide, etc. You will get still higher, and you will have to do multi-junction. I am not a device physicist, beyond that I don't know. But there are a whole lot of work, and if you see that particular slide, different work, I have given the reference for each one of them. There are a lot of people who are working on how to increase the efficiency for solar panel. But remember, efficiency of solar panel does not help you get cheaper power, does not help you in powering your home better. I want to point that out. In fact, lower cost, lower effect. I don't mind from 15% it goes to 13%. Let the cost goes down from 38 rupees to 30 rupees. If it goes down to 25 rupees or 20 rupees per watt, I am ready to accept 10%. Doesn't matter. All that it means that my solar panel size will slightly go up to 10 meters square. So what? For a kilowatt. So really doesn't matter. Okay? Anybody else wants a question? Yes, there is a. Please.
You were talking about insulation and effective temperature. Is there any relationship between insulation and effective temperature of the solar panel?
Yes, higher the insulation, solar insulation means higher the sunlight, temperature will go up higher. That's fairly obvious. And if on the other hand early in the morning, if sunlight is small, the temperature will be lower. So sure, if the insulation, if the sunlight is higher, brighter, you will get higher temperature. It's fairly related. But all that it really means to you is a few percent.
Won't that affect the efficiency?
It does by a few percent. So in the brightest sun at noon, when the sun is brightest, you get from 200 to 1000 watts per. So your amount of power goes up by 5 times. And then you are saying because of high temperature it goes down by 5%. So instead of going up by 5 times, it goes up by 4.75 times. That's not bad. At 200, early in the morning, you get 1/5 the sunlight. 200 only. You get temperature is not high. That time you get pretty much the same full power. So you get that, but you get 1/5. So instead of getting it 5 times, you get 4.75. Doesn't really matter. So that is not the primary correct. Yes, that's a loss that you must know will take place, but should not bother you. You want more sunlight for solar panel. Alright, and it's a secondary effect. Even putting water pipes, etc., will increase your cost from 38 rupees to 60 rupees. And then you will get 5% extra. That's not where you should save. You do a better DC-DC converter, not put DC-DC converter, use direct DC devices. That's where your cost will be saved. Our problem is we keep on looking at wrong things. which doesn't impact life. If you want to see the impact of life, the total cost that matters. Okay? Is that okay? Thank you. I think, is there anyone? There is one more college which is asking question. Vasavi?
Single phase AC, which is 220 volts operating voltage, what is the ideal operating voltage for solar? Is it 12 volts, 24 volts, if you want to have for distribution? First question, sir. Then second question is, for example, if you want to put it for household, for small operating things like lights and fans is okay. But if you want to operate air conditioner or refrigerations, which take very high current at the starting, is it not going to have a severe effect on the solar panel? So how do we stabilize the voltage there? And how we should design the things such that it can withstand that high starting currents? Thank you, sir.
Okay. So I think you have some very interesting question, and I wish I was there in front of you to discuss this in more detail. But let me try to answer questions. First of all, if you are operating at 220 volts and you have to have a AC, you are doing 220 volt AC. So you have to have a solar panel which will produce DC. You have to do a DC to AC converter. When you are doing a DC to AC converter, and you have to probably do conversion to from whatever voltage of DC to convert it to 230 volt AC. So you can convert from 400 volt DC to 230 volt AC. You can convert from 100 volt DC to 230 volt AC. You will require converter, whether you use buck converter or boost converter, it really doesn't matter. The losses will be there, as I pointed out. If it is a low wattage like a half a kilowatt, you will have a loss about 15 to 18, probably 20%. If you have 100 kilowatt, the losses will be much less, 3% or so. So it really doesn't matter. If you need AC 230 volt, and your solar panel is at whatever voltage, all that it means your converter design will change. It's a buck converter. Normally a buck converter is easier to design than boost converter, but only marginally. I think at higher, it really doesn't matter. So your first question is as far as that is concerned. The second question is very interesting. Second question is, lights and fans may be okay, will require low power. What about air conditioner and refrigerator? Well, first of all, refrigerator does not consume more power. If you look at refrigerator, what is the power that it consumes? Refrigerator, even a current AC refrigerator may consume 200 watt, 250 watts, but 250 watts it runs for about 30% of the time. So if you look from whole day, it is equivalent to consuming 80 watts throughout 24 hours. So it doesn't consume. Air conditioner does consume much more power. Now, what I am going to do in the on Monday is talk about trying to power the whole home using solar DC instead of solar AC. Why? As I pointed out, not lights and fans, all the lights and fans power consumed goes down by a factor of 2. And if you don't use AC DC converter, you get another 20-30% advantage. So even if you use refrigerator or use air conditioner, I'll say if you use DC, BLDC motor, you can reduce the low total power consumption by at least 30%, maybe 35%, 30-35%. So you save significantly. Now, the only problem is that they may not be easily available today, but it's a matter of time. I think you can develop them in 2-3 years time, they will be available widely. Lights and fans have started become available. 2 years back, they were also not available. Now, even the air conditioners and the refrigerators will all be available, DC ones. Already some are available, small numbers, but more will be available in the next couple of years time. Now, when you do that, then can you do it at solar DC? And then what should be the solar DC voltage? What I will propose in the next class is that we should operate at 2 voltage. One is at 48 volt, another is at 380 volt. So as long as the power requirement is of the order of 1 to 2 kilowatt, probably you can do it 48 volt. 1 kilowatt you can do it 48. If your power requirement is 5 kilowatt for DC, remember the DC power or even 2 kilowatt, 3 kilowatt, you may want to go for higher voltage like 380 volts. So that's a kind of thing that we will propose and we will talk about it in the next class. Alright. I know I partially answered, but by the end of the next class we will be able to answer this question much. So can we go to the next lecture please? Next lecture is on batteries. For the batteries, I will first start looking at the performance parameter, state of charge and state of health. Then I will do broad classification, types and comparisons and charging. The later part are less important. Performance parameter is what I am going to spend more time on. Now remember, why batteries? When solar is to drive the electrical load, remember the solar is not available throughout the day, it is available only in the daytime, and even when it is available the power fluctuates. Suppose we connect solar directly to a load. Every time cloud fluctuates, the amount of power available will go down. What will happen? Every instant of time when you produce, there is a generator and there is a load, the two must match. The power generated must match the power consumed. Every instant of time. If it doesn't happen, it doesn't work. The voltage will either keep on going up, going down if power consumed is more than power produced, and the whole thing may suddenly trip at certain point, something may fail, and that's not easy. That's not easy. Exact matching of the load and power produced is not easy. Now when you do it all over the country, or you do it for, let's say, whole of a state, there are large number of users. Even if they are changing the usage, there is more or less certain average load, and you have to ensure that you are able to produce that load. If there is slightly more, you actually reduce the amount of power that is being fed. You can handle that. But if it is at each home level, every time solar slightly reduces, what do I do? Every time I turn on, turn off a light, my load increases or decreases. What do I do? So load minus solar power need balancing. Load minus solar power. If load is larger than solar panel power, then somebody else has to supply. Who can supply? Well, if grid and solar panel are connected together, grid can supply. And suppose my solar panel produces more than the load, then theoretically solar panel can feed the power to the grid. So grid is a source as well as a sink. Of course, for reverse feeding, you have to worry about, because you need to exactly synchronize it, and if there are large number of people reverse feeding, there can be possible problem. But at least grid is a large source or large sink. It can take care of small variation. If you are putting a 500 watt panel and if it reduces a bit or increases a bit, alternatively you can use a battery. Now battery is a storage which can take in power, which can give you power. So if you have battery, in fact grid does not matter. Extra solar panel power, if there is solar power is higher than the load, it can feed the battery, and if it is less, battery will. And you can even combine solar and grid and still feed. If you put a battery, it can either charge or discharge. So battery is extremely important for local use, balancing of power. The only problem is battery power is very expensive. Very expensive. We'll give you the thing in the end. Grid power is not expensive. Today solar power is not expensive. Battery power is very expensive. So every time you feed into the grid battery and take it out of the battery, the cost goes up. So you want to minimize that. If on the other hand, if you feed into the grid and take from the grid, there is something called net metering, in which case you only get charged for the amount of net power that you consume. Yes, but if millions of people start feeding into the grid, grid will never be stable. And small power producers feeding into the grid, things will not work. You can of course take from the grid, it's less or more power. So the ideal solution will be take from the grid, take from the solar and put a smallest possible battery. So yes, extra solar is there, feed into the battery. But if less solar is there, take as much from the grid as possible. If there is a power cut, take it from the battery. That's a kind of thing that we were going to talk about. Of course, the other very important thing about the battery is that it makes it portable. This, without battery, it will not work. My laptop will not work without battery. And portables are very important today. So battery becomes extremely important. Now, how do you define battery capacity? Battery capacity is defined either in terms of watt hour. How many watts? So suppose I say it's 100 watt hour. What does, it's like your 100 watt hour. What does it mean? It will give you either 100 watts for 1 hour. 100 watt hour. 100 watt hour means either it will give you 100 watts for 1 hour, or it could give you 10 watts for 10 hours, or 1 watt for 100 hours. Sometimes of course the voltage is fixed. Suppose voltage is 10 volts, suppose voltage is 20 volts. Suppose I use voltage is 20 volts. Voltage I put as 20 volts. So battery of 100 watt hour is equal to 5 ampere hour. 5 ampere hour at 20 volts. 5 ampere hour, that means if I can put 5 amperes for 1 hour, or 0.5 amperes for 10 hours, or 0.1 ampere for 5 hours. So sometimes it is given in terms of ampere hours with the voltage given, but the better handling is watt hour. I have here given you example of 1 kilowatt battery or close to 1 kilowatt, 0.96 kilowatt battery, and it is a 48 volt 20 ampere hour battery. Or it is a 24 volt 40 ampere hour battery, or 12 volt 80 ampere hour battery. All is 1 kilowatt hour battery. 1 kilowatt hour battery basically is essentially can store energy equal to 1 kilowatt hour. Now 1 kilowatt hour is very important because 1 kilowatt hour is also called a unit of electricity. 1 unit of electricity. That is 1 unit of electricity which you can draw from the grid. It costs approximately 5 rupees. So 1 kilowatt hour battery can store theoretically 1 unit of electricity. Alright. So that is the capacity. Capacity is the first important thing that we need to. The second important parameter is called rate of charge or discharge. How fast are you taking power out of it, or how fast you are trying to charge it. Discharging time, how fast are you taking? And it is measured in terms of C. This is not capacity. Capacity, this is charge rate or discharge rate. Charge or discharge rate. 0.1 C. So suppose you have 1 kilowatt hour battery. That's what I have given, 1 kilowatt hour battery. 1 kilowatt hour battery, and I says 0.1 C means 0.1 into the capacity. That means I am charging or discharging at 100 watts. 100 watts. Okay. Okay. So if I am doing at 48 volt, it means I am charging or discharging at 2 ampere. Suppose I put 0.2 C, it means I am charging, discharging. C is the capacity. Capacity is 1 kilowatt hour. So 0.2 C means I am charging, discharging at 200 watt. 1 C means within 1 hour I am going to either empty the battery or fill the battery. 2 C, in 30 minutes I can charge the battery completely from 0 to full or full to 0, discharge it. Now this is extremely important. For example, suppose I am driving a car, electric car. I am going to get an electric car next week. I am going to drive, all of you are welcome. I will drive you. So in the electric car, if I charge, so suppose my battery becomes totally zero, car stops. And if I charge it at 2C, in half an hour it is fully charged. But if I charge it for 0.1C, I will require 10 hours to charge it. So in fact, I recently was in China and I saw some two-wheeler. And in 5 minutes, they are charging 50%. 5 minutes, if it is charging 50%, what is a C? Can somebody tell me? 5 minutes, 50%. Yes, 5 minutes, 50%. In 5 minutes, 50%. Can one of you answer? 5 minutes, 50%. So in 10 minutes, it will be full charge. So how many C? Come on now. 6C. 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 So charging, discharging at 6C. Now charging, discharging of 6C is possible for small batteries, not at large. We will look at this whole charging rate, discharging. So if I have, for example, a battery can be fully charged in 30 minutes, it's at 2C. The next important parameter is called state of charge. What is the state of charge? How much is it charged? If it is a 100% charge, it's 100% SOC, fully charged. 70% SOC means it is a 70% charged, very simple. 0% SOC means completely empty. Fairly clear? State of charge is very clear. Next is depth of discharge. Now this is an interesting thing. Depth of discharge essentially basically means, do you know what happens? Depth of discharge is a parameter, basically implies, suppose the battery is fully charged, how much will you discharge before stopping to work and charging? It's a parameter that is defined. For example, in laptop battery, remember that once you reach about 10%, it gives you warning and says stop, 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 can't work. It's a 90% depth of discharge. You don't want to go further discharge. Why? Because if you discharge more, you can damage the battery. So depth of discharge has to do something without damaging the battery or its lifetime. So for example, depth of discharge of a lithium battery, the kind of battery that we use in our cell phone today or in laptop, is about 90%, probably even 95%. But after 90% starts giving you a warning, you can go, and if you try to go below 5% or 4%, it shuts you off. Keeps on giving you a warning. You're going to danger zone. Please stop. Save your work. I can't even save your work if you go below. Otherwise, all these laptops are designed to save everything. Who is doing that? Operating systems is designed for all that. But you normally shouldn't discharge more than 90% if you want good life of the battery. If it is a VRL or lead acid battery, I'll come to that later on. Lead acid battery. You want good life of the battery? DOD should be 50%. Don't discharge for more than 50%. Occasionally it doesn't matter, but don't discharge. It is like, to some extent, suppose you are running and you are discharging your energy. You are discharging your energy. How long before you should take some glucose? Suppose you are running a marathon. At a certain point, you should take some glucose. Why? Because at that point, if you take glucose, you can go double, again take glucose, again to go that much. Suppose you run 2 kilometers and at that time you don't take glucose. In 200 meters maybe you will fall down, and then taking glucose doesn't help. You understand that? But that time if you take glucose, you can run for another 2 kilometers. Again probably you have to stop and take a glucose. Now 2 kilometers, it depends. Aditya can do it for 4 kilometers. And if I ask somebody else, he may not be able to do for more than a kilometer. I'll need a glucose every 500 meters. Okay? So that is called depth of discharge. Below that it will start damaging. Now, damaging, what is damaging, how, it varies, lifetime. If you impact the battery adversely, you impact the lifetime of the battery. So typically depth of discharge is a very important parameter. Depends on the kind of battery and what is the life that you want. If you don't care about the life, you discharge immediately, completely. How does it really matter? Once let it run. But the whole idea is these are rechargeable battery. Remember, you want to recharge them, then you don't want to spoil the life of the battery. But now comes the battery lifetime. Now a battery, and I am talking about only rechargeable battery, I am not talking about single charge battery. Single charge battery life is one charge discharge cycle. One time you charge, discharge finished. A battery lifetime is maximum number of charge discharge cycles before its capacity degrades so that it cannot be used any further. Now what does it mean by cannot be used further? Well, that also varies. What does it mean by cannot be used further? Becomes highly inconvenient to use it and rather dispose and change the battery. Now it will depend on application to application. For example, laptop, if I am running it and suppose I bought a new laptop, new battery, nicely, 6 hours it is running. After some time it is running only 4 hours. I may still continue. The life, it has come down, degraded. But I will keep on charging, discharging. Then sometime I am left with 2 hours. Now I have to start worrying, because if I go somewhere and don't get enough power, I have to start worrying. If I am driving a car, suppose a car is 100 kilometer distance, and that is when the battery was new and everything was fine, and the battery has gone down to 85%. Now I can only go 85 kilometers. I have to keep on remembering. Now I can't go beyond 85 kilometers. After some time, I may not be able to go more than 70 kilometers. I'll better replace the battery, because for me 100 kilometers was important. So it is a number of charge discharge cycles. Now, number of charge discharge cycles lifetime is a function of two parameters. Depth of discharge. For example, if you take a lead acid battery and if your depth of discharge is 80%, the lifetime of the battery, number of cycles, charge discharge cycle will be very small. For example, we often buy these two-wheelers, it comes from China, imported, and we allow it to depth of discharge of 80%. In 300 cycles, battery has to be thrown. On the other hand, depth of discharge is 50%. Now I can run it for 1000 cycles, maybe even more. The second parameter is rate of charge discharge. If I am trying to charge and discharge fast, I will spoil the battery lifetime. I will spoil the battery. If I am charging slowly, discharging slowly, battery will last for a very long time. So remember that I said, should I charge it for my car in 30 minutes or 10 hours? If I charge in 30 minutes, yes, it will work. My lifetime of battery will go down like anything. If I charge in 10 hours, my battery will last long. For example, the car that I am going to get, if I charge it at 10 hours or even 6 hours, it will go on for 3000 cycles. If I charge such that charge discharge can take place in 1 hour, probably I won't get more than 1000 cycles, even less. The question also sometimes comes, what if I normally charge in 6 to 8 hours and sometime charge if required with in 1 hour? How does it impact? Well, the answer is somewhere in between. Clear answer is not available for this. I think we need experiments. In fact, we are asking the battery center that is being set up at IIT Madras to actually carry out these kind of. So it varies, but the two things, depth of discharge and charge discharge, I can't just do anything and expect the lifetime to be same. Lifetime is defined. Somebody, a battery manufacturer says, I'm giving you this battery has 2000 cycles as long as rate of charge discharge is not more than 0.2 C. Both charging and discharging also. I can't even take out the power too fast. 0.2 C. 0.2 C is good. And if the depth of discharge is not more than 65%, then it can go 1500 cycles. If you are ready to do 80%, then maybe it will only go 1000 cycles. So the two parameters matter a lot. So this is the example. If the lifetime is 10,000 cycle, battery will come to an end 100 days if it charged 10 times a day. Take 1000 days if it charged once a day. If depth of discharge exceeds the rated depth of discharge, it will decay much faster. And if charge discharge rate is higher, it will decay much faster. How much faster will vary from the kind of batteries. So battery charging and impact on lifetime. Is it good to keep charging the batteries even after it is full? Certainly no. Your overcharging will damage. So should you keep your laptop plugged in? Well, really doesn't matter because your charger will take care that it doesn't overcharge. Your charger has to design, you can keep it plugged in, but the charger should ensure that it doesn't overcharge. Charging the battery right amount of time and for right duration becomes critical for battery lifetime. Equally important is to keep monitoring what is the status of the battery, what is the state of charge, and how do you really handle it. There's careful design of battery chargers, so you don't overcharge, don't charge unnecessarily very fast, are very, very critical. Well, other thing is battery status. Lead acid battery, open circuit voltage is directly proportional to state of charge. So if you take the battery, suppose it is not feeding, disconnected, keep it for some time, though somebody will say keep it for 6 hours. You don't need to, probably even if 15 minutes it will kind of stabilize, and then you measure the voltage, the open circuit voltage and state of charge. If open circuit voltage is 12.8 volts, a 12 volt battery, it is fully charged. If open circuit voltage is 11.7 volt, it is fully discharged. So for lead acid battery or VRLA battery, it is much easier. You can measure the open circuit voltage and figure out state of charge. The alternate method is what is called Coulomb counting. You keep count of how much ampere has gone in, how much ampere has come out completely, and then it will give you state of charge. But you have to keep on a battery management system. It keeps on monitoring all the time, charging and discharging. Calculate every electron that has gone in and gone out. Of course, it will give you state of charge. In fact, that's what the laptop does. Laptop has a lithium battery. Lithium battery, you can't do this. So it actually monitors how much time you charge, how much time has been discharged totally, and keeps on giving you, and then gives you a warning saying now it is 85% or 21 minutes, 10% remaining, 90% has gone. It can go on, but it will start damaging better charge. The other interesting question that somebody had asked me, I have this battery, I have been using it. Can you tell me how much more will it last? Age of the battery. The number of charge discharge cycle remaining for it to continue to function well. Suppose for me working for 6 hours without power on my laptop is very important. When I bought it, it was pretty much working 6.2 hours. I want to continue to work for 6 hours. I've already used it for 8 months. How much lifetime of my battery is left? And there are methods of doing what's called state of health. State of health tells you how much have you used your charge discharge cycle and how much you still have to use. And there are ways to measure state of health. For example, you can completely discharge and then charge it and again discharge it and measure what is the total capacity. The capacity will keep on changing. Capacity, full capacity is related to the state of health. Alternatively, so this is periodically complete discharge and then take it out and find out the route. So these are matter of details. I don't want to get into this. There are other ways of measuring it. You can, for example, measure the internal resistance of a battery, not for all battery, but for certain batteries. And you will find that if internals, if the percentage of battery life, if it is abnormal cell, it will just either can fall down like this. So normal cell, you will see that the impedance keeps on increasing with the battery. And this is a percentage change. And for weak cell, it increases very rapidly. So if it's this, that means cell is normal. This cell, and now you have to take the overall battery into account and do this. Self-discharge rate. Now if you keep a battery, if you charge it and keep it in the shelf, how long does it, what will happen? It will start discharging. How fast will it discharge? After a month, you come and check. It's still 95% full? Well, not bad. So, for example, primary lithium metal is at 10% in 5 years, so it hardly discharges. Alkaline 2 to 3% per year. Alkaline is 2 to 3% per year. Lead acid 5% per month. Charge it in 1 month 5% if you don't use it. So you don't use it for 4 or 5 months, it will have significantly discharged. Nickel based lithium is much worse. Well, 10 to 15% in 24 hours, first 24 hours, then 10 to 15% per month. So this is also important, self-discharge of battery, and you can do all these tests. Why only some batteries can be charged and some cannot be discharged? Well, depends on what is electrode and electrolyte. I'm starting to get into battery chemistry, and I'm not planning to spend too much time. The material is here, material and chemicals used determine whether it is a reversible or irreversible. There is a definition of primary batteries. It is irreversible, one-time charge. Secondary batteries can be charged, discharged, charged, discharged, etc. These are the primary batteries: zinc carbon, heavy duty zinc chloride, alkaline, lithium, silver mercury oxide, and used for toys, recorders, photo flash, watches. But these are batteries that we are interested in: secondary battery, nickel cadmium, nickel metal hydride, lead acid, lithium ion polymer. And more, we are working more and more on this. Nickel cadmium etc. is used, but less. I have got the chemistry. Lead acid, there is an equation: lead plus lead dioxide plus twice H2SO4 gives you lead sulfate plus water. So electrode is lead oxide, another electrode is lead, and water is the electrolyte. Actually, it is H2SO4 converted to water. So what happens? Initially it is H2SO4. After some time it becomes water. So then you have to replace that. That was the old type where you kept on filling the acid. So that is one of the things. Then this is getting into how do you really take each. So you take these electrodes, the 2 electrodes and electrolytes that I talked about. You actually put electrodes and electrolytes in each set of plates. So that, and I think there's a better picture. Yeah. So you take one cell, one set of one set of electrodes and electrolytes. That's the first thing that you take, cell, and then a separator plate between one cell and another cell, and then you put them together and you form what is called module, and you put more modules together and you form what is called pack. So you form multiple elements together and form a module, and then multiple modules together you form a pack. And these has to be all done. You have to worry about the conductors and every single thing, and then filled with electrolyte. Pack is filled with electrolyte and possibly a battery management system. Remember that you may want to do coulomb count, you may want to control how fast it charges, discharges, etc. You may want to do it. If you don't, then battery management system is not a part of the battery, you may put it outside. Within lead acid itself, there are three kinds. One is called flooded battery. This is the old battery that used to have there. 10 years back you had to keep on filling acid. But I think nowadays you have what is called VRLA, AGM or gel, absorbed glass material or gel. These are sealed batteries. You fill it once, you don't have to refill it. So you don't use sulfuric acid, but essentially absorbed glass material or gel, and using that you can make a sealed battery. These are very commonly used battery. VRLA batteries are one of the most commonly used. VRLA AGM is very, very commonly used. Lithium batteries, another battery found all around us, very lightweight, much larger capacity, greater power in smaller packets, relatively low self discharge, long life, and there are variants, lithium ion, etc., etc. But if you look at what does it really tell us, look at these numbers. If you take nickel cadmium battery, charge time is 1 hour, but it's fairly reasonably heavy, and the peak drain can be high, optional drain can be 1C. Discharge per months are very high, 20% and 30%. So these two have gone because of that. Lead acid and lithium ion batteries, on the other hand, if you look at discharge rate per month, is not very high self discharge rate. Lead acid can do 1,000 cycles if you do 50% discharge. Lithium ion can do 3,000 cycles if you do 80% or even 90% discharge. Density is extremely good for lithium ion, so the future is lithium ion. And cost, etc. also, of course, lead acid is extremely low cost. Lead acid VRLA battery you can get around 6,000 rupees per kilowatt hour. 6,000 rupees per kilowatt hour. But remember that you can do only 50% of the discharge, so it comes to only equivalent to half kilowatt hour. So if you take real 1 kilowatt hour, it's at 12,000 rupees. Lithium battery on the other hand more like 17,000, 18,000, but you get more number of cycles. There are various charging methods, and I'm not getting into various charging methods. These are important. There are trickle charge, constant voltage, pulse charging where you charge positive and then you charge negative. Why do you do that? You are charged positive, you generate some heat into this. You don't want to continuous charge. Heat becomes so much of a problem that it can cause damage to the battery. You stop charging. Either you can just stop charging, wait for some time and again put another pulse, or you even do what's called negative pulse, discharge pulse, that essentially kind of shakes the whole electrolyte and makes it more uniform, and it gives you a better life. So all these are various methods. Even though the battery may not be usable in one application because of the required state of health, it may be usable in another. So secondary use of battery, extremely important. Particularly you start with a battery which is using in vehicle. It is started with a new battery, 20% of capacity has gone down. What does it mean? That instead of 100 kilometers, it is lasting only 80 kilometers. Which means if a truck was supposed to go and deliver goods all the way to a certain place and come back, now it cannot do that. So you have to replace the battery. But the battery has not got spoiled. You can now use it, let's say for home usage, secondary usage. You don't care as much, even though now the size will become larger. At homes or offices you can start using it. You can do a third reuse where you sort of say, well, even offices don't want to use it, but maybe some other place can still be used. Now this more or less my last slide. What do we really need to consider when we want to look at batteries for Indian homes? Affordability, usability, suitability for solar solution. Now affordability basically gives us two candidates. The most important is lead acid battery around 6,000 rupees with 50% after discharge. Lithium ion with higher number of cycles, around 15,000 rupees, but 15,000 rupees is not available as easily, now closer to 22,000 rupees. But if you see, if you take, and this can do 90% depth of discharge, so if you really look at it, it's 12,000 rupees, but initial sum cost is small, so sometime you still, lead acid is still considered the favorite. Lithium is coming up very quickly, cost is going down, in years to come maybe lithium will take over. Usability is rechargeability. Lead acid, as I told you, that at 50% depth of discharge you can do 1000 cycles, but there are now variants available where you can do 2000 cycles at maybe 7,500 rupees. That's not bad. And lithium ion maybe 15,000 rupees can go to 2,500 cycles, 3,000 cycles. But for solar, you know, even a 1500 cycles is 5-6 years. You may want to anyway replace that. Suitability, both these things are possible to do direct DC integration. Reduce for small losses. Smart BMS will be required if you use lithium ion. Active monitoring and management may be required. Well, that's pretty much, I've done it at a fast pace, the second lecture, which I was supposed to take more time, and I come to the quiz. And I hope this time you get it right. When batteries are operated beyond their depth of discharge, their lifetime is reduced, lifetime is increased, cannot be charged anymore, reaches a balanced state. It's like asking a question, if a duster falls, does it go up or does it go down? Such a trivial question. I'm sure everybody will get it right. I have which college? Runta. Where is Runta College from? Runta College, I am looking at you. Answer. Which one is right? A. How many of you believe A is right? Lifetime is reduced when batteries are operated beyond depth of discharge. Runta, please give me an answer by raising hands. How many of you believe A is right? Lifetime is reduced when batteries are operating beyond depth of discharge. I see one person raising 2 hands, rest of the people are not raising hand. Second person, lifetime is increased. How many of you believe lifetime is increased? I don't see anybody raising hand. Answer C, cannot be charged anymore. If you charge beyond depth of discharge, it cannot be charged anymore. How many of you believe C is right? How many of you believe reaches a balanced state? Nobody is giving right answer, at least here. How many of you believe A? So A is the right answer. That is the right answer. I see some hands. Second question, what are the methods used to determine state of charge? There is a voltage method, intrinsic method, impedance method, self-discharge, Coulomb counting. You give me all the right answers. Can A be used for state of charge? Those who believe A can be used for state of charge. Voltage, measuring the voltage, you can find state of charge. Yes or no? Raise hand, those who believe. Alright. Those who believe B is right, intrinsic impedance can be used to measure state of charge. Intrinsic impedance cannot be used to measure state of charge. Self-discharge, can it be used to measure state of charge? Coulomb counting, can it be used for measuring state of charge? 1%, 2%, 3%. There I see people standing up instead of raising hand. So the answer is A and D. A and D. So the first answer was A, second answer is A and D. Alright. So I think we'll stop here today, and if there are questions we can answer questions, and then we will take over next class where we'll start designing the system. Questions? Anybody has questions? with many states now adopting net metering. For residential, what role battery would play? Well, I believe that net metering is not that great a solution. Many states are jumping for it because somebody is trying to sell net metering. After some time, people will realize that if lots of people use it, of course, small number of people use it, it doesn't matter. But if lots of people use it, it will give rise to grid instability, and then somebody will come and disconnect everything. But only if a few people use it, it may work. So if you have used net metering and got solar panel, you pray that others don't use it. All right. There is a second question. Will help understand how solar generated power injected into the grid via net metering. Well, transmission distribution losses, all kinds of issues will come. In fact, it's actually a, so you know what happens if you are generating a lot of power, like if you are putting a 20 kilowatt solar panel and then you are generating excess, you can feed it to the grid. I don't think that will cause problem. Because number of people who will put 20 kilowatt is very small. Remember, 1 kilowatt will cost you around 38,000. By the time you end up, it is more like 60,000. So 20 kilowatt will be about 12-13 lakhs. And most of us will not spend 12-13 lakhs on a solar panel. You won't even have roof space. Very, very few people, some corporates will use it. So if they use, numbers are small, it will work quite well. It can be managed. But if large number of people start using it, it's a problem. If the people who are using 1 kilowatt start using it, it's going to be a problem. I think fools are sitting there because some vendor is trying to sell something. State government after state government I have seen making a fool of themselves. The only thing is that they put it, hardly any person, very, very few people use it, then it's okay. Nobody has really in world worked out for small producers. See, large ones are no problem. See, mostly people try to copy Germany or United States. Everybody there uses 20 kilowatt, 10, 30 kilowatt, 10 kilowatt. In India, people use half a kilowatt. That's where the problem is. Okay, any question? No one has any questions? What is the chroma effect or skin effect? In the, or skin effect, at least I know it's the same thing or what. So what happens when you do transmission, high voltage transmission, what will happen, power will actually flow only on the skin, not in the core. If it is a AC power, if it's a DC power, it will go into the core. So if it only flows in the skin, it sees a limited amount of conductor. So your resistance increases, your losses increases. In a DC power, it flows through, so it sees the full conductor, so its resistance is less, losses are less. Thank you very much. I think we'll stop here.